This is the thread pool sample. In this presentation, I'm going to show you how to use thread pool objects, both by using the thread pool class and delegates to do asynchronous operations. I tried to keep these samples as simple as possible just to demonstrate mostly the syntax and the process by which you spawn threads rather than get into a complicated task that is more difficult to understand than the actual process of launching the threads. In the beginning here, you see in the main function, we have a console window height property being set and a buffer height property being set. And the only reason I'm doing that is to maximize the screen size without actually having to set the properties once it runs. Then, as you can see here, I have two methods I'm going to call, delegate threads and worker threads. One thing you're going to note is these will accomplish basically the same thing using the same types of resources. However, they have distinctly different ways of executing the threads and getting them started. So let's take a look at the delegate threads method, which follows main. In this method, you can see here I'm creating a func delegate called factorial with a lowercase f that points to a method called factorial with a capital F. So what we're doing here is we're taking this factorial method and assigning it to this delegate. If you look at the definition of this func delegate, you can see the input for this function. There's a single input is of type unsigned integer, and then big integer will be the result. Now, big integer is a data type provided by the .NET framework. You'll find it in the system.numerics namespace that allows you to create arbitrarily large integers. And since it stores its data in a binary format, it's actually quite fast. As a matter of fact, factorial is a notoriously slow algorithm to calculate if you don't take any shortcuts. Well, I actually had to, in the factorial method, if you hit F12, you'll see I had to put in an artificial delay because the big integer object is just a little too fast for you to see that a thread is actually operating. So while we're here, let's take a look at what factorial does. It accepts a value of type uint, and as long as the value is greater than 0, we create a big int or a big integer and set it equal to 1, and we're calling it fact. And then we loop from I equals 1 until I is less than or equal to the value passed in, and we multiply fact by I, essentially, and assign the value back into fact. That's what the times equal will accomplish. Once that's done, I put an artificial sleep in here, which will suspend this executing thread for 4 seconds. That's what the 4000 stands for, is 4000 milliseconds. And then I'll return the value. If a bad value is passed in, I simply return 0. So by hitting Control minus, I'll jump back to where I was. So you can see that is what this delegate is going to do. Now, to execute this delegate, there are several ways I can do it. I can use this syntax as you see here, which is saying on that delegate dot begin invoke. I could also say dot invoke, which would be a synchronous call, but the point of this operation here is to demonstrate asynchronous calls. So what begin invoke will do is put this delegate onto the thread pool, and it will execute as soon as a resource is available. If there are no threads operating currently, then it will actually start executing pretty fast. Also note here I did a console write line to say that the factorial delegate is started, and to press enter to continue, and then it'll wait for a read line. When I'm running the demonstration, you'll see that there is a delay. Then it'll output the factorial results, the 4-second delay which I put in there. And then I can output thread pool info. I think it would also be interesting to output that here as well, So you can see if there's any change between the time I say begin invoke and the time after the console read line has occurred. Then another possibility here is to start the delegate threads, again using begin invoke, but this time I'm going to call a different method. Okay. Oh, actually, let's go back up a little bit. I skipped over one key feature in this begin invoke call. Notice here I'm passing base num to begin invoke because that is the input for the function. The second parameter is of importance. Factorial done is the method that will be executed when this particular delegate has completed its task. So when I say factorial.begin invoke, you pass it this, and if we had 7 different arguments being passed to the method, then there would be it, listed here, followed by the final 2 parameters, which are going to be the callback method. As you can see, that's what pops up in IntelliSense. And then finally, in this case, some state value. This can be whatever you want to pass. Okay, this could be the time of day. This could be a reference to this delegate as well. So you could pass the factorial delegate. You can pass whatever you want. It's simply, if you look here at IntelliSense, it's simply an object that you can pass. You can see here it says object right here, object. It can be whatever you want. It's state information. To get that state information, let's go to factorial done, and you can see here this iasync result IAR. By the way, this is what the callback method for worker threads is when you're using the begin invoke syntax. This is basically the state information, and to get it out, you cast this IAR into an async result object, and the async result object, if you look at its properties, has many different things. Is completed, await handle, so that way if you want you can use some of the synchronization techniques to wait for completion. But the important thing here is this async state. That corresponds to that last parameter in the begin invoke method. And remember, it was an unsigned int, so I can cast it to an unsigned int and retrieve the value as such. Now, to get the value out of this particular callback, because we need this callback to retrieve the result, what we need to do is on this delegate, and as you can see here, I can get out of the AR property the async delegate as well, which was the delegate that was fired with the begin invoke method call. I will take that, and remember this is the delegate that was fired or was executed to perform the factorial method, and I will retrieve del as such. From there, the corresponding end invoke command can be executed on that delegate to retrieve the return value. In this case, I pass it IAR, which was the input to this function. Now, yes, this is a fairly long-winded way of retrieving the results. But what I can do here is make life a little simpler for you and say AR dot async state is the last parameter passed to begin invoke. So you can remember what that is. And then here, AR dot, rather than type it in, contains the delegate that was executed. So the method that was executed to get us here. And then finally, to get the delegate's result, call del.end invoke, passing it IAR. Okay, so this is a pretty typical method for retrieving values from an asynchronous method call using the begin invoke syntax. So let's go back up to the top where we were. You can see our delegate threads. That pretty much will take us all the way to this code here. So we've done the begin invoke on the factorial. Then I'm going to create 24 worker threads. Okay, so for I equals 0, I is less than 24, I plus plus. As you can see here, I create a different delegate. This time I'm calling it del to be real creative. It accepts an int, returns an int, and it points to the sample thread method. If we go to sample thread, it's pretty simple. Basically, it does a loop from 0 to a very large number, in this case 100 million, and then it just returns the ID that was passed in. You know, this isn't a very useful method at all. It's basically a method to sit there and just do busy work to show you how the thread gets created and how it executes. So basically, I'm going to invoke this delegate those 24 times, passing it I, which is 0 through 23. So that's kind of like the ID of this thread. It's not a real ID, it's something I contrived here. This is the callback, sample thread done. So let's take a look at that. Again, we're getting the async result object. We get the delegate from that async result object by getting its async delegate property. And again, it's a func int and int because that was the definition of sample thread. Returns an int, accepts an int. Returns an int, accepts an int. And then we're just going to say thread something is done. Since it's returning the ID that we contrived and passed to the thread, that is the return value from that particular thread. So when we execute end invoke, it's going to return that int, as you can see here in the function call, because that is what it is. That is the return type, int. And it's going to execute that and print that out. So let's go ahead and run the application in its current state so you can see how this works. So you can see here we have that press enter to start the delegate threads demo. Let me bring us back to that code page here. Okay, so right now we are in the wait state, waiting to start this delegate threads method. So as soon as I execute it, remember what's going to happen. I'm going to do the begin invoke of the factorial method, which is going to delay for an artificial 4 seconds, and then I'll print out thread pool information. After 4 seconds, the factorial will return, and then I will hit enter to continue, and then I'll print the thread pool information once again. As soon as that's done, it'll begin executing this chunk of code, which will spawn 24 worker threads using the del begin invoke syntax. And then we'll see them start up and terminate. Okay, so let's go back to the code here, the execution, hit enter. So as you can see here, while we're waiting for the factorial to complete, when I retrieve the thread pool info, I'm just reporting the maximum number of threads available. Okay, so we have 1023, and then notice here, as the code is executing, it tells us that we have 1022 available. that means we have one thread executing. Now, one thing to note about how the thread pool works is it tries to accomplish all of the thread pool execution in as few actual physical threads as possible, also known as managed threads. So basically what happens is in the thread pool, it will create a dedicated thread or a managed thread, and it will use that thread to manage some other sub-thread worker methods. And basically it allows them to execute and complete. Remember, the point of using the thread pool is to have short running or very small methods that are going to execute and not live very long. So they do their work and then they terminate. So unlike managed threads, which are intended to be long-lived threads, these are supposed to be very quick running threads that all work in the context of one master thread or one managed thread. Now, how that actually works is not as critical as understanding how to put it together. Okay, so if I hit enter, it's going to perform those 24 begin invokes on those kind of like dummy methods just to show you the object spinning up and spinning down. So as you can see here, it spawned these threads. And notice here the number of threads available at every step started at 1022, then it went to 1021, and it stayed at 1021. There is a good reason for this. I am on a dual core system here. And on a dual core system, I have two physical threads available for me. Now, if I was running on a multi-core system like a 4-core system with virtual threads enabled, then I would see this number possibly different. Now, that doesn't mean because I have 1,022 threads available that I'm actually going to use that many. In fact, I don't know if it's physically possible. This is just what .NET 4 defaults to. Again, when you're using the thread pool, it is going to manage these threads for you, so you don't really ever have to worry about this number. So I'm going to terminate this application now. That way we can see the next part of the code, which is the worker threads portion. Now, an interesting thing about this is we are going to pretty much accomplish the exact same thing we did before, except instead of using the begin invoke syntax, I am going to use the queue user work item syntax. Now, an interesting thing about the queue user work item syntax is that, like the begin invoke, I can pass to it the method I wish to execute, but notice I didn't have to wrap it in a delegate first. And then I pass it some values based on this particular method here, the factorial worker. Let's go take a look at factorial worker. And you can see here it accepts an object called value. Now, unlike the begin invoke syntax, with this particular method, I only get a single parameter passed in, and it's always of type object. So this is basically a state value that I can pass to this thread. The difference is, again, if I have to pass it multiple values, I have to combine them into some object, maybe like a property bag or some class I create, which is simply a set of key value pairs, or you can use a dictionary, whatever it is you want to use to pass the values, but then you have to extract them out of this value object into their original components. So if I go back to the code, as you can see here, I'm saying execute this method factorial worker, passing it some state value. In this case, I'm passing the value 50. Again, this can be any object. So it can be my student object. It can be a list of objects. It doesn't matter, but I'm only allowed to pass one thing. Okay, let's go back to the method again. Now, as you can see here, I'm doing pretty much the same thing I did earlier with the factorial as far as the functionality is concerned, and I again have the artificial delay. The biggest difference, however, look at the factorial worker definition. It does not return a value, whereas factorial does return a value. That is another difference in the way you will execute these thread pool objects. Because what's going to happen is we have this factorial worker executing, and when it's done, it's done. Notice if we go back to the call, you can see here we queue the user work item. Let's take a look at the different ways to call it. Okay. Notice here it says wait callback. You might think, oh, that's what it executes when it's done. No, in fact, that is the method to execute. Notice here we have no other callback. What that means is when this object is done executing, or this worker thread is done executing, we don't really get a notification. So unlike, again, the begin invoke, where you do get a notification in the form of a callback method, this one, when it's done executing, it's simply just done executing. So when I'm executing this factorial worker, instead of actually returning the result of the factorial, what am I going to do? I am going to just output it right to the console. Now, there are obvious ways you can work around this. For instance, you can, in the object passed in, leave a property or several properties aside for return values. So you could have, let's say, my thread object or thread info object, and that thread info object could have things like, in this case, the base number that I'm passing in, but it could also have a result property, so when it's done, you can assign that. Then, back in the console, if you're waiting for that to complete in the main thread that executed it or spawned this subthread, you could simply wait for that object that you passed. Instead of a 50, it'll be some other object. You can simply wait for that to change, or you can use an auto or manual reset event, so when that thread is done executing, it can set or fire the event so something else can be notified that it's done. So there are definitely ways around that, but if you like the ability to have a callback method to be called once the thread is completed executing, then by all means the begin invoke syntax is probably the simplest way to go, comparing these two together. Now, at another time we will talk about the TPL, or the Task Parallel Library, which is another way to spawn threads. The difference is it has better syntax and better handling for return values from these thread pool threads. So, the factorial worker, pretty straightforward. It outputs onto the console when it's done. So let's go back to our worker threads. And again, we're going to do the 24 queued items, but instead of using begin invoke, we're just going to do the queue user work item. As you can see here, we're going to call work item, whereas before we called sample thread. We're going to call work item. So if we go to that definition, as you can see here, it's pretty much the identical thing from the identical method as sample thread. The biggest difference here, as you can see, again, since we're using the thread pool methods to launch this thread, we're getting an object for its parameter. So when I want to output the ID, I have to cast that state object to an int before I do that. And again, notice in the other example, when we did the begin invoke, we can return the ID, which we can respond to in the end invoke. But since we're using the thread pool objects, we have to output it onto the console or do some other handshake with another thread to indicate that we've completed. So in this case, I'm just taking the simple way out, because if I really wanted a return value, I would have used begin invoke and end invoke. So let's go back up to the top here, and what I'm going to do is I'm going to comment out these 3 lines here so we don't perform the first test that we already did, and then I'm going to run, and then we'll look at the worker threads demo. Again, the factorial worker thread starts. 4 seconds later, we'll get the result. There it is. Notice here it says press enter to continue above the factorial output. It spawns those 24 items. You get the exact same results, 1022 and then 1021 for the rest. And all of them have completed. We hit enter, the program completes. Now again, this is a very rudimentary sample for how to spawn worker threads or thread pool threads, and it's not meant to be anything sophisticated. As we do other demos, such as the synchronization demos, you will see more useful threads and how they interact with each other. So we'll have multiple threads, like maybe producer threads and consumer threads, so you can see how they interact together rather than just the simple fire and forget type approach.